So today we'll look at another application of SVD, and that's called multidimensional scaling. Multidimensional scaling is when you have a lot of sample points, their distances are given. The mutual distances between any pair of points is given, okay? And you have a whole lot of points. And then from the distances, how to find the coordinates of those points. That's multidimensional scaling, and you'll see how. I will also provide a little demonstration. Okay, so we have, let's say, data samples. There are n number of data samples, and the dimensionality of each sample is d. Okay, and I'll use xn to represent the nth sample, and each x is a d by 1 vector. And then since this is a column vector, by default everything is a column vector, I transpose them to get a row vector. And then I take all the x transposes together, 1 through n, and I get this matrix, uppercase X, which is an n by d matrix called the data matrix. Okay. Now, you know that the mean of all these points is 1 over n, since we have n points of summation xn. Right? So that's the mean xn. And this is the data matrix. This is what the data matrix looks like. Each row is a sample point xn. This is the mth row, lowercase m, is x transpose m, the transposition of the point xm, the mth point, and likewise the nth row contains the transposition of the nth sample point. So this is a n by d matrix, data matrix. Here's a little example, x1, x2 until x5. We have 5 two-dimensional points. And so this is the data matrix, uppercase X, it's 5 by 2. And the average or the mean of the x's is, if you can compute it, it's actually -1 plus 1. Okay. The Gram matrix, or the raw Gram matrix, G is X transpose, which is this matrix here. Okay. This I'll define the Gram matrix. Basically, it's X times X transpose, which is this 5 by 5 matrix here, because we have 5 sample points. So this is X, and this is X transpose. G, the Gram matrix, is defined as XX transpose. So at row M of the Gram matrix and column N, what we are doing, we are taking X transpose M, this row, and this column, XN, and then we get XM transpose XN, which is this scalar. This is GMN. GMN is in the mth row, nth column of this matrix G, and that's equal to X transpose M, XN. Okay? This is the Gram matrix. Okay. Now, centering the data. So these are our data points again, X, N, where N is from 1 to uppercase N. We have N samples. Centering is we do this translation, take every point and subtract the mean from it. So X bar N is the centered sample point. This is the raw sample point Xn. Once we subtract the mean, we get X bar N. Okay. Now, what's the average or the mean of all X bar n's? It'll be 0, right? That's why it's called centering. So we are shifting it by this amount so that the mean of the x's now becomes 0. So these are the X bar n's, the centered points. And equivalently, this is what we can do for the whole data matrix. X bar, uppercase bar, is equal to X minus 1 over n, 1 transpose X. Okay, now I'll explain this why in the next, just in a minute. Let's define this H to be equal to I minus 1 over n, 1 transpose. And H can be shown, you can easily see that this is a symmetric matrix because H transpose equals H. In which case, X bar equals X times H. Okay, now why does this work? Maybe I'll use the whiteboard. So 1 is a vector of n ones. Okay, let's say we have two-dimensional points, and I'll call them x1, y1, oops, then x2, y2, x3, and y3, and then x4, y4. This is my X. Okay, what's its mean? X1 plus X2 plus X3 plus X4 divided by 4, Y1 plus Y2 plus Y3 plus Y4 divided by 4, right? Now, 1 transpose is a matrix of all ones, n by n matrix of all ones. Okay, when I do this multiplication, what do I get? First, this will be a 4 by 2 matrix, right? So this will be x1 plus x2 plus x3 plus x4. x1 plus x2 plus x3 plus x4. I'm right-handed and sorry, I'm left-handed, and this is a right-handed cursor. That's the problem. What's the next element here? First row, second column. Y1 plus Y2 plus Y3 plus Y4, right? Y2 plus Y3 plus Y4, correct? And when I do 1 over 4, n equals 4 in this case, I have 4 points. So what do I get? So I'll multiply every element by 1 over 4. So this becomes 1 over 4. This becomes 1 over 4. Oops, sorry. And now in the second row, I'll again get these, right? Because I'm again multiplying 1, 1, 1, 1 with all the x's here, and then 1, 1, 1, 1 with the y's here. And then when I take 1/4 of that, again, I'll get the same thing, correct? So basically, this is mean of the x's transposed, correct? This one, the first row. And so what I'm doing here is I'm repeating this transpose of the mean n number of times. Okay, so this is 1, 1 transpose. This matrix of all ones. Okay. So this is what I just showed you. This is each of these rows of this x here is a sample point transpose, right? And then from that, you're transposing, excuse me, you are removing, subtracting x hat transpose, okay? And so it's equivalent to doing this operation, the transpose of this operation for each row. I hope I was clear with this. So we get the centered data matrix. And once we do the centering, we know that the mean is now 0, the origin. And this centering operation we can do in this manner. We can define this matrix H equals, so this is just X. So I take the identity matrix here and then minus, so I'm subtracting the mean, -1 over n, 1, 1 transpose. This is a matrix, n by n square matrix of all ones. This is H. And so X bar is equal to H times X. This is how I did the centering operation. Okay, and we'll remember this. The expression for H equals I minus 1 over n, 1, 1 transpose, and centering operation is done by pre-multiplication with H. So Hx gives us the centered X bar. And also remember that X transpose is equal to A because H is a symmetric matrix. Here is an example. So this is X. And so once I do the centering, I get, this is whatever I get from the centering. This is my H. And then this is X. So this is the centered data, X bar. This is the centered data matrix. And you can look at the, what's the mean? What's the mean of the, in the X coordinate? Sum of all this is 0, right? And likewise, the sum of all these is also 0. So the mean is 0, 0, the origin. Okay, any questions so far?
No, it's clear, Dr.
Okay. Okay, now the centered Gram matrix. Again, we define the centered Gram matrix as X bar transpose. And again, as before, so X bar, the mth row will contain the centered mth sample, X bar transpose n. And this column here, each column will be a sample. The nth column will be X bar n, centered sample n. Okay, and then when we do the multiplication, this is the scalar entry of this matrix G in the mth row and nth column. That's X bar transpose n, X bar n. And remember that this is a n by n matrix. Okay, next we define another matrix, the squared distance matrix. D, the squared distance matrix. Okay, remember it's squared. So this is the square distance matrix. It's also another n by n matrix. And in the mth row and nth column, dmn squared is the corresponding entry, and that's xm minus xn transpose xm minus xn. So it basically, this is the norm of the difference, xm minus xn, correct? And that's equal to the distance. So basically this is dmn square is the square of the distance between the 2 points, not to be confused with the Gram matrix. The Gram matrix, at the same place we have x bar transpose mxn. Okay, and here in the distance matrix, it's different. This is uh, the distance between them squared. Okay, now let's expand this. So dmn square is equal to xm minus xn transpose xm minus xn, which is equal to, I'm opening the parenthesis, and so noticing that each of them is a scalar, xn transpose xm will be equal to xm transpose xn. And so I have dmn squared is x transpose m xm plus x transpose n xn minus twice x transpose x mxn. Okay, all I did was open up the two brackets here, which is equal to, now, if you look at the definition of the Gram matrix, remember, this is what we have. GMN, either if you take X bar, then you get G bar, or you can take the raw X's, in which case you get X transpose MXN would give you GMN. So either way, the centered data points or the raw data points, either way. So what happens is, now this is what we saw, and this is what we expanded. Now this is the data matrix squared. So excuse me, the distance matrix squared, and this is GMM plus this is GMN from the Gram matrix, and this is -2 GMN. You'll remember this. DMN squared equals GMM plus GMN minus twice GMN. Okay? So let's remember this. And here's an example. X bar is this. This is the centered Gram matrix, G bar. This is the centered data. And so this is our G bar. This is what we'll get a 5 by 5 matrix here. And the distance matrix is very completely different from the Gram matrix. In fact, the diagonal elements of the distance matrix will be 0. Or these are the square distances. Okay, this will be the distance matrix, and you can compute the Gram, whatever the Gram matrix will be. Why are the diagonal elements 0? Because the distance from a point to itself is 0, right? What's the distance between points 1 and 2? Here 5 and here 1. 5 squared, 25 plus 1 square 1, that's 26. So the square distance is 26. Okay. So now MDS. In MDS, suppose we have the square distance matrix. We don't have the coordinates of the individual sample points. All we have is the distance matrix. Okay. So then what we do, so this is the square distances. Okay, so this is known. And we need to find the data points X. We'll assume that the sample points are centered. So X equals X bar. Okay, and we have to find the data points. What do we do? The trick is to first find the centered Gram matrix, which is uh, X bar transpose. The first step is to find the Gram matrix. So we get the Gram matrix, and assuming that the sample points are centered, this is equal to G bar, which is X bar transposed. So we'll get from the square distance matrix, we'll get this Gram matrix. And then what we'll do is, this is the first step of MDS. And then from this point, from this Gram matrix, how to obtain the centered sample points will be the next step. This is the first step. From the square distance matrix, we'll get the centered Gram matrix. And we will show that G bar equals negative half HDH. So this is basically how you implement this step. All you do is take the distances, find H. H is, you don't need the data points to find H. So find H, and then you get this. G bar equals negative half HDH. Okay? And so this is what we'll show next. So this step. And then from the centered Gram matrix, we will be able to obtain the centered sample points. Okay, so this is the square distance matrix D. Its nth element is dmn squared. But we already showed that dmn squared equals gmm plus gnn minus twice gmn. Okay, this is what we already showed. Now let's take the diagonal elements of the Gram matrix, G11, G22 until GNN, and form this vector lowercase g. This is this vector, G11, G22 until GNN. Okay, are you guys with me so far? We saw this expression before.
Yes.
So this is all the diagonal elements I take and define my lowercase g. Okay, now what am I going to do? My goal is first to show this part, right? And this will establish how we do this step, the first step of MDS. So this is my G, and then, okay, this is what I'll prove first. First step of my derivation will be to prove this. Okay, so this is my G. So G1 transpose, 1 is a vector of all ones, will be equal to basically, first row will be all G11 ones, right? The first element of this G is repeated n times. So this is G11, G11, G11. The mth row of G1 transpose will be GMM repeated n number of times. And likewise, the last row will be GNN repeated uppercase n number of times. So this is my G1 transpose. Likewise, my 1G transpose is equal to, each column will be G11, G11, G11 repeated n times, GNN lowercase n. The nth column would be this, GNN repeated this many times. And the last column, the uppercase nth column, will be G uppercase n repeated this many times. Basically, G1 transpose, if you take the transpose of this, you get 1G transpose. And the transpose of this matrix here is this matrix. Okay, so this is G1 transpose, this is 1G transpose. And this is what I'm going to prove. See, you see this G1 transpose here and 1G transpose here. Okay. So now let's look at what the left-hand side of this equality that we're going to prove is, so G1 transpose plus 1G transpose minus twice of G, the Gram matrix, is equal to this. This is G1 transpose. This is 1G transpose minus twice of G. Here you have all the elements intact. G11, G12 up till G1n, and then Gn1 until Gnn, right? This is the entire Gram matrix. Now let's look at what's the mth row going to look like when we do this operation. This plus this minus twice of this. Mth row, okay, here, and nth column. Okay, we're going to find out what this Gmn what will be in the mth row and nth column of this whole thing. So that will be Gmm plus Gnn minus 2 Gmn, right? We're looking at the mth row everywhere and the nth column.
Right.
So it will be, that entry will be Gmm plus Gnn minus twice Gmn, which is equal to Dmn squared, because we've seen this before. Okay, so this gives us Dmn squared. G1 transpose minus, plus 1G transpose minus twice G gives us this, D. This is the square distance matrix. Okay? So this is what we just proved. Now let's move on to the next step of the derivation, which will be to prove the first step of, establish the first step of MDS. So let's remember this expression because we'll use it in the next step. So this is what we will prove now. That G equals negative half HDH. We just showed this. Now, if we assume that the data is centered, then X equals X bar, right? The data is centered, and likewise G equals G bar. Okay, so this is what I just showed, and we know the expression for H is equal to this. Now, what's H? Let me multiply H with this. H1G transpose is equal to this H times 1G transpose, which is equal to, this is the identity matrix. So this is, the first term is I times 1G transpose, which is 1G transpose, negative 1 over N, 1 transpose 1G transpose. 1 transpose 1G transpose. Now, what is 1 transpose 1? 1 is a vector, n-dimensional vector of all ones. So what is 1 transpose 1?
1.
No, it's n, right?
Oh, yeah. N.
Right. And
N, this uppercase N. 1
so
transpose
n
1 is,
cancels now.
what's that?
I'm saying n cancels now when we do this. Can we cancel this n?
Can be, yes, that's what I'm going to do
Yeah.
in the next step.
Right.
So that's 1G transpose minus 1G transpose, which is equal to 0. So H times 1G transpose equals 0.
0.
What's this? Okay, so H1G transpose equals 0. Now, I'll take the transposition of this. So G1 transpose H is also equal to 0. 0 transpose, right?
Yeah.
So H1G transpose equals 0. G1 transpose H equals 0. Okay, let's remember these two. And I got this by doing the second expression by simply transposing both sides of the first. Now, so this is what I have so far. This is the result that I got from step 1. And now I just showed that G1 transpose H equals 0, H1G transpose equals 0. Now I'll prove this. So I'll take the right hand side, negative half HDH equals negative half H, and I replace D with this expression here. H G1 transpose plus 1G transpose minus 2G times H. Then I open up the parentheses. So I get the 3 terms. What will be the first term? So this will be the first term, right? Negative half H G1 transpose H. What's G1 transpose H?
These terms are 0.
0. Second term is 0.
Okay.
Right? So this negative half HDH equals HGH. Okay. Which is equal to, now G is equal to XX transpose. Correct? And so replacing G with XX transpose, this is what I get. HX, X transpose H. Also remember that H is a symmetric matrix. So H is equal to H transpose.
Right.
So this is equal to, and remember what's HX? The centering. When we did the centering, X bar was equal to HX, right? So this is HX, that's X bar, and this X transpose H, which is the same as X transpose H transpose, is X bar transpose. Correct? And so negative half HDH equals X bar transpose, which is
G
bar.
bar.
So this is what we do. G bar equals negative half HDH. Okay?
Yes.
And so if the square distance matrix is given to us, then we can easily compute the centered Gram matrix using this expression.
Can I ask a question?
Sure.
So what is making these terms to be 0?
We just proved it, right?
Yeah, but what conditions makes them 0? Because at the left-hand side, we have HDH. So what has to be 0 for the above terms to be 0? Like we have G1 transpose H is equal to 0, right?
Yeah.
So what has to be 0 there for, or there is no constraint on H or G?
No.
There are no restrictions. Okay.
It's the property of this H. H is a matrix such that if you take any vector X, X1 transpose H will be equal to 0.
Yeah.
By the definition of H.
Yes.
Okay, the matrix H has been constructed in that manner.
Okay.
Maybe I can do a little Matlab demo right now. So let's, oops, I closed that window. I shouldn't have, but let me do a little demo. So are you seeing, never mind. I'll open Matlab. Let me go to Okay. So let me create, edit MDS demo. X equals, let's take rand n comma d. This is n equals let's say 100 points and d equals three-dimensional points.
Mm.
So this is my x, and then let's plot them. Let's compute the mu. Mu of x is equal to mean x. Okay, then let's plot, it's three-dimensional, so plot x comma 1 comma x all comma 2 x all comma 3, and let's plot little circles in blue, and hold on, grid on, and then plot 3. I'll then demo what the centering does. Mu x1 mu x2 mu x3, and we'll plot them maybe pentagons or hexagons or in H and in red. I'll call this figure 1. Let's run this. So I have my sample points. I have 100 sample points. Each sample point is three-dimensional, and this is the center. You can read off what the coordinates of the mean is 0.5, 0.475, 0.49, whatever. Okay, that's mu. Now let me get the center, the H matrix. H equals I n comma n minus 1 transpose. I'll just write it as ones, and this is a matrix of all ones over n. Okay, so this is my H matrix. And then X bar equals HX, correct? And then now let me go to figure, actually, let me mu X bar is equal to mu X bar. Let's do just this step. Oh, H star. Okay, now mu X, what's mu X, the original mu X? This was the average of all samples, right? Well, actually the transpose, which was, if you go to figure 1, where is figure 1? It's this point here, right?
Yeah.
Okay. Now, for some strange reason, I cannot see the, okay. Now let's see. Okay, so this is mu x. Now what's mu x bar? All zeros. 10 to the negative 16. So basically it's all zeros,
Yeah.
right? And you can see that. So if you can plot, so let's take figure 2 and plot the x bars. And we plot all the x bars together. Mu x bar 1, mu x bar 2, mu x bar 3. And then we run it. Oh, what was the...
We have an error because mu x bar 2 is.
Oh, thank you. Mu x bar 2. So this is the original sample points. And so you can see that the x-axis, notice the x-axis is from 0 to 1, y-axis 0 to 1, z-axis 0 to 1, right?
Yeah.
Now, if you go to figure 2, it's the same as this figure. The shapes are the same points. Actually, let me juxtapose them. So this is my figure 1, and this is my figure 2. This is the raw samples. These are the centered samples. Oh, I think figure 2, I did it twice or something. Did I? Let's do figure 1 and figure 2 again. Okay, now it's clear. Basically, these are the same points. In figure 2, you have the same points. This is x bar and this is x, right? The only difference is, see the range of x, y, z are between 0 and 1, 0, 1, 0, 1. Here, it's between -5 and plus 0.5. Okay, and the center is now 0. 10 to the negative 18 is, so this is very close to 0. Okay, so that's the centering operation. And this is my H. This is what the H looks like. In fact, let's take only 6 points. And maybe, well, why did I do this? Let me just see this. Let's say n equals, not 6 points, even just 4 points. And then I'll compute my H. So what's my H now? It's a 4 by 4 matrix. This is my H. Okay. And I take any vector x. Okay, so x, oh, G will be diagonal H, right? I forgot the expression. Was G equal to diagonal H? No, it was the diagonal. No. What was it? What? Sneak peek. Kind of hard to. Okay, it was H1G transpose. Okay, so what I'll do now is something. Okay, so this is my, now let me go, it's a little cumbersome to navigate when I have all these. Okay, this one. G1 X transpose. Was it G1 X transpose or which one was it? Well, do you guys remember?
No, just looking at the slides now, trying to.
Okay. Can you just tell me which one was equal to 0?
We were looking for
H1 G transpose. So H star ones 4 1 star X. Oh, X. You see, you get all zeros, right? Okay. So in fact, H times 1 trans 1 is all zeros. Okay. Okay. So going back to the slide. So basically H1G transpose, H1 is all zeros and G1, sorry, 1 transpose H is 0. Okay. So now, so this was derivation step 1 was kind of redundant. Yeah. Okay. So slide show. Okay, so this is 0. So derivation step 2 is actually relevant. So this is step 2 of the derivation. Right. I just realized that H1 was equal to 0 right now. Yes, it is. Otherwise, when I did the derivation, I didn't realize that. Anyway, so now we have G bar equals negative of HGH, which is X transpose H, which is the centered X bar transpose, which is G bar. Right. Okay, so G bar equals negative half HDH. And we'll highlight this as the first step. Okay, so step 1 of MDS is to find the centered Gram matrix from D. This one. Now let's proceed to step 2. Step 2 is to obtain the spectral decomposition of G. Let G be equal to V lambda V transpose. Okay. Now I will later on, I'll show that this G Gram matrix will have only its positive definite, so its eigenvalues will be all positive. Therefore, if lambda is the diagonal matrix of all eigenvalues, you can just take the square root of the diagonal elements. They'll also be positive, and you'll get X equals V lambda to the half. Okay, and so then you can retrieve your X's. So this is how you get your X. Okay, and this is, I'll demo that to you. So this is the note on the Gram matrix. So G bar equals XX transpose. And I'm going to show that it's positive, definite. Okay, G plus G bar transpose equals XX transpose, which is XX transpose. This proves that it's symmetric. So G is symmetric. And then it has real eigenvalues since it's symmetric. We've seen that. Real symmetric matrix has real eigenvalues. Any symmetric matrix has real eigenvalues. Now we have to show that it's positive semi-definite. We take any vector V, B transpose G bar V is equal to B transpose XX bar transpose V, which is equal to X bar transpose V transpose X bar transpose V, which is the L2 norm squared of X bar transpose V. This is a vector X bar transpose V, and this is the L2 norm of that, which is greater than or equal to 0. So this V transpose G bar V is always greater than or equal to 0 for any vector V, which means that G bar is positive semi-definite. So it's symmetric, positive, semi-definite. Okay, and so it has non-negative eigenvalues. So this is the spectral decomposition. All these are non-negative. And then what we do, this is an n by n matrix. We take the square root of this, and this is our X bar. Okay, going back to MATLAB, let me show that to you. Again, back to MATLAB. So clear. So now let me run this again. Now what I'll do is I have G, right? And then what I'll do is I or Ix. Ix gives you only the first 6 eigen values, eigenvectors. So AK, so A largest, K largest eigenvalue. So I want all the eigenvalues. And then let's just do this. I have my G, right? Oh, I don't have G. So what I'll do is, so I have my X bar. So G equals X bar star X bar transpose. This is actually G bar. And then what I'll do is, I'll do VD is equal to I's G bar. So I want all of them, so 100. Okay, and then D equals D dot star 0.5. I take the square root. Okay, let's do these steps first. This is my G bar. And then I do the spectral decomposition of G bar. Okay, and so these are my eigenvalues, R and D. These are the eigenvalues. I could have displayed them here. So the eigenvalues are in D. These are the eigenvalues. Okay. Why is eigenvalue negative? Oh, it's basically zero. These are all zeros. Okay, so negative is due to numerical, but they're basically zeros. And
Why?
that's true.
Why do we have this much of
Value zero.
values? Because we have n as 4. I think we defined
No,
it.
no, no. I
Okay,
run
it's
this
100
again.
again. Okay.
So this is 100.
Yeah. Okay, now that makes sense.
Okay, n is 100.
Right.
But the rank of x bar is how much? 3,
3, because the lowest of both.
right? So x bar transpose, g bar will also have rank 3.
3, yes.
Okay, yeah, so rank, that's why all these eigenvalues are zeros.
Yeah.
Rank equals the number of non-zero eigenvalues.
Right.
So G bar.
D, it was D. Oh, yeah. G bar, yes.
Okay, now VDV transpose will be equal to G bar, right?
Mm-hmm.
Oh, I already did half of that. So let's say G2 equals B star D star D transpose. Oh, B transpose. And this G2 will look, this is G2 and this is G bar. Are they the same? G2 is the same as G bar, right?
Yes.
Yes.
Okay. So now what I do is I'll take the square root of this. Okay. And then what I'll do is, so this is my square root of D. Okay. And x2 is equal to V star D. Okay. One point, since I was taking 3 dimensional vectors, the rank is 3. Okay, so D is a 100 by 100 matrix, but the rest are all zeros. Okay, so D equals D all comma 1 to 3. Okay, and then I do my x2 equals VD.
Mm.
In general, 1, 2, 3. Well, this D was, let's call it dim. So dim equals 3, and so this is D equals, no, this is D. Let's call it S or lambda. Lambda, and then x2 then we'll just remove the dim plus 1 through n, all those columns. Okay, and so then x2 equals V star L. In fact, we can do these operations in this sequence. X2 equals, and then figure 3 figure 3, plot these. Never mind the means, we didn't include the means. Okay, so now let's run this. So figure 3 is basically we retrieved the x's back from once we have this. Okay, this is figure 3. Figure 3 is the same as figure 1, right?
Mm-hmm.
No, it's not. Oh, it's not scaled properly.
I just Dr. Das, there is a step where we say L is equal to 1 over 2L. Why do we multiply by 1 over 2?
Okay, so let's go back to the.
Yeah, I'm just wondering if that is.
So basically, this is what I got. If I had taken the number of dimensions to be 1,000 or something, more than the number of sample points, then I would have gotten a low-dimensional representation of L. So just hang on. We are. I want to share the right. Are we? What screen are you looking at? Are you looking at?
We're looking at the slides. Yeah, the PowerPoint slides.
Okay. So what was your question?
So my question, like here we have the like to the power 1 over 2, but in simulation we are multiplying by 1 over 2 with the lambdas.
Yeah. So this is what it is. I took the lambda. This is L.
Right.
So lambda to the half.
Yeah, that's my question. Here we have to the power 1 over 2.
Yeah.
Okay.
If x is v lambda to the half.
Right. Right.
Then this x bar is this. Then x bar x cross bar transpose will be g, right?
Okay. Yeah.
So we retrieve the x from the gram matrix and that from the distance matrix. Now in the Matlab demo, I use d first as the dimension and then as
Okay.
the matrix of eigenvalues.
Okay.
But don't get confused.
Yes. Yes. Yes.
Okay, so this is the scale was different. That's why it wasn't exactly of the same shape. XYZ coordinates. I could have used X lim, Y lim, Z lim, but I didn't. But anyway, so you got back the X's from this D.
Right.
Okay, and in this figure, you see X is low dimensional. In fact, suppose you have high dimensional data. Okay, 1,000 dimensional data. You want to visualize them in 3 dimensions. What you do is, what you can do. So we saw this. This is the gram matrix. Okay, you have very high dimensional data, so all the eigenvalues will be positive. None of them will be negative. And then what you do is eigenvalues are non-negative and in decreasing order. The lambda 1 is the highest, lambda 2 is the next highest, then lambda 3 and so on. So as we progress in the bottom right direction, we'll get progressively smaller and smaller entries in lambda, correct? And so you can simply, when you do this, you can simply drop the lowest eigenvalues, which is actually what we did. We just took the first 3 eigenvalues, right? We dropped all of this entire block we dropped. And so this gave us a reduced dimensional data matrix, X bar. In fact, since we started with 3-dimensional data, that's why we got 3-dimensional, we took 3 dimensions. But if we had started with very high dimensional data, then what we would have effectively done is reduce the high dimensional data into just 3 dimensions. Okay, so for dimension reduction, so we get the high dimensional data, the distances from them, and then we do find G bar equals minus half HDH, where H is given by this, and then we do the spectral decomposition of G bar, drop the lowest eigenvalues, and then compute X bar equals V lambda transpose, lambda half. So what happens is we took very high dimensional data and then we reduced it to, we dropped the lowest eigenvalues, we took the top 3 eigenvalues, let's say, then this will give us 3-dimensional points. But it will give us 3-dimensional points in such a manner that the pairwise distances between the points are preserved as much as possible. Okay, the pairwise distances in the high dimensional data is somewhat preserved even in the low dimensional data X bar. Okay, any questions?
No.
Okay, so with this we end today's lecture, and any questions, or do you have any other questions? Anyway.
Hi, Dr. Das. I have a question. Like, what are these applications? Like, where we will do apply all these methods?
Multidimensional scaling is a very classical statistical technique, and that's used in visualization. For instance, you have high dimensional data, and you want to visualize them, or it's not, you don't have data, all you have is, let's say, pairwise distances, okay, between sample points. For instance, the data is not in terms of vectors. The data could be like DNA samples of different people. Okay. And then you somehow find a method to compute the distances between them. Pairwise distances may be equal to number of mutations from one DNA to get to the other DNA, minimum number of mutations, or something like that. So devise your own data matrix.
Okay, yes, I can understand.
And then you can project those points in 3 dimensions. So that will give you a good visualization of how the DNA samples of these individuals look like. It will give you who are related to, how closely related they are to one another, and so
on. Yes, yeah. That's not sure.
Okay.
Yeah.
Okay, so any other questions?
No.
No.
Okay, so we'll end today's lecture and we'll begin. This ends this first block of this course, block A, which is linear algebra, with a review, and then we have the exam. I have moved the exam date because I want the exam to be, let me stop the recording.